So good morning all of you. So in this video lecture we will be discussing mathematics of cryptography, and this we will cover our part 3 and the primes and related congruence equations. So these are the objectives which we are going to cover in this lecture. So prime numbers are commonly used for asymmetric key cryptography, and this topic of prime is very large in terms of number theory. And in this chapter we will be discussing some of the important topics related to the prime numbers. So the prime numbers can be divided into three groups. Among the positive numbers we have this number 1, which is exactly has one divisor, and then the primes are those numbers which has exactly two divisors, and then we have the composite numbers which have more than two divisors. So a positive number is a prime if and only if it is exactly divisible by two integers, and that is 1 and by itself. So if we talk about the smallest prime number is 2 itself, which is divisible by 2 and by number 1. Then if we are asked to list all the prime numbers smaller than 10, so there are basically 4 prime numbers less than 10, which are 2, 3, 5 and 7. And it is interesting to note that the percentage of primes in the range 1 to 10 is 40%. The percentage decreases as the range increases. So if we talk about the cardinality of prime numbers, that is how many prime numbers exist, whether there are a finite number of prime numbers or this list is infinite. So we can say that there are infinite prime numbers, and there has been defined a limit on the number of prime numbers. So here by this equality we can define the number of prime numbers for a number n. So pi of I n denotes the number of prime numbers. So this lower limit was discovered by Gauss and the upper limit was discovered by Lagrange. So as an example, suppose assume that there are only primes are in the set 2, 3, 5, 7, 11, 13 and 17. Here p is equal to this much and p plus 1 is equal to this much. So but we know that this 51051, this can be written in terms of these prime numbers, and none of these primes were in the original list. Therefore we say that there are 3 prime numbers greater than 70. Similarly, if we are asked find the number of primes less than this much, 10 to the power 6, so the approximate range is about this much. The actual prime numbers are 78498. So now the question comes how we can test whether the number is prime or not. So given a number n, we can test it by using this by checking all the numbers which are divisible by numbers less than root of n. And although this method is inefficient, but it is a good point to start. So there is a theorem that if n is composite, then n has a prime divisor less than or equal to root of n, and here is the proof of this theorem. So let us take pure example. Suppose we want to check whether 97 is a prime number or not. So first of all we will calculate the root of 97, and we will take the floor of it, which will come out to be 9, and the prime numbers less than 9 are 2, 3, 5 and 7. So we will test, or we will divide 97 by these 3, 4 prime numbers and we find that 97 is not divisible by any of these prime numbers, so that is why it is not a prime number. One more example, if is 301 is a prime number. So again, first of all we will calculate the square root of 301 and we will take off floor of it, so that will come out to be 17, and then we will prepare the list of prime number less than 17, which are 2, 3, 5, 7, 11, 13 and 17. And we can see that the numbers 2, 3, 5 does not divide 301, but 7 does. So therefore 301 is not a prime number. The next important topic is the Euler's phi function. So this Euler's phi function is also sometimes referred to as Euler-Torsion function, and it plays a very important role in cryptography. This function basically finds the number of integers that are both smaller than n and relatively prime to n. So there are basically 4 sets of rules which helps us to find the phi of n. The first rule is that phi of 1 is equal to 0. So we know that 1 is the smallest number, and any number less than 1, and there is no number exists which is relatively prime to 1. So that is why phi of 1 is 0. Then phi of p, where p is a prime number, is equal to p minus 1. So this is quite obvious since p is a prime number. So all the numbers which are less than n are relatively prime to n, p. Then phi of m cross n, where m and n are relatively prime to each other. So this is equal to phi of m multiplied by phi of n. Okay, but the main condition is that m and n are relatively prime to each other. And the fourth is that phi of p to the power e, where p is a prime number. So this is equal to p to the power e minus p to the power e minus 1. So in this manner we can compute the Euler's Torsion function. So let us continue with this topic, and what we can do, we can combine the above 4 rules to find the value of phi of n. For example, if n can be factored like this, that n is equal to p1 to the power e1, p2 to the power e2, and pk to the power ek, where p1, p2, pk are all prime numbers, then we can easily combine the third and the fourth rule to find the value of phi of n. So in this manner we can combine the third and fourth rule to find the phi of n. And it must be noted that the difficulty of phi of n depends upon the difficulty of finding the factorization of n. So if it is difficult to find the factors of n, then automatically calculating the phi of n also becomes difficult. So let us take some example. So first example is, what is the value of phi of 13? So it means that we need to find out all the number less than 13 which are relatively prime to n. So since we know that 13 is itself is a prime number, so we can apply rule number 3, and we can easily say that phi of 13 is 13 minus 1, that is equal to 12. Next example, what is the value of phi of 10? So here 10 is not a prime number. So what we will do, we will make use of the third rule, and we will divide phi of 10 as the product of phi of 2 into phi of 15. And now both phi of this 2 and 5, these are both prime numbers. So then since these are prime numbers, so we can easily apply rule number 2 and can say that phi of 2 is 2 minus 1 and phi of 5 is 5 minus 1. So 1 into 4, that is equal to 4. So so number of prime numbers which are less than n and relatively to prime are 4. So let us take one more example. What is the value of phi of 240? So we can write 240 as 2 to the power 4 plus into 3 to the power 1 into 5 to the power 1, and now we can apply rule number 4, and we can compute phi of 240 as 64. So similarly take one more example, phi of 49. So in this case you may be tempted to factor 49 into equal to 7 into 7, but we cannot apply this rule, because in that rule suppose this is m and this is n, so the rule was that m and n should be relatively prime to each other, but since 7 and 7 are not relatively prime to each other, so we cannot apply this rule. So what we will do in this case, that the third rule applies when m and n are relatively prime to each other, so we need to apply the fourth rule. So we can write 49 as 7 to the power 2, and now we can compute, since 7 is a prime number, so 7 to the power 2 minus 7 to the power 1, so that is equal to 42. So this will be the correct answer. So one more example, what is the number of elements in Z14 star? So that is basically equal to calculating the Euler-Torsion function on 14. So we can factor 14 as 7 into 2, which are relatively prime to each other. So this will come out to be 6. So there are basically 6 numbers, that is 1, 5, 9, 11 and 13, which are relatively prime to 14. And there is an interesting point that if n is greater than 2, then the value of phi of n is even. Next important theorem in cryptography is Fermat's Little theorem. So it is a very important theorem, and it plays a significant role in number theory and cryptographic system. So there are basically two versions of this theorem. The first version is that a to the power p minus 1 is congruent to 1 mod p, so where this p is a prime number. Okay, and we also assume that a is an integer such that a does not divide p. So there is another assumption in this theorem that a does not divide p. Then we have the second version. So this second version removes the condition on a, and this second version states that a to the power p is congruent to a mod p, so where again p is a prime number. But the restriction of the first version, that is a does not divide p, has been removed. So let us take few examples how we can use this Fermat's Little theorem to compute the explanation. So let us try to compute 6 to the power 10 mod 11. So we can see that this is the form of a first version of Fermat's Little theorem, that is a to the power p minus 1 is congruent to p. So that is why we can write p equal to 11. Another example to find the result of 3 to the power 12 mod 11. So in this case you can see that the exponent 12 is not equal to modulus 11. So what we can do, we need to substitute, do some substitution so that it can be solved using Fermat's Little theorem. So the substitution goes like this, that we can split 3 to the power 12 into 3 to the power 11 into 3 to the power 13. So this will be the split. Then we can compute and divide it into 3 to the power 11 mod 11 and 3 mod 11. So now this becomes the form of Fermat's second theorem. So this is equal to 3 and into 3, that is 9. So the result will be 9. Another important application of Fermat's theorem is to calculate multiplicative inverse quickly if the modulus is prime number. So if p is prime, we can quickly calculate the inverse. Okay, so if p is a prime and a is an integer such that p does not divide a, then a inverse mod p is equal to a to the power p minus 2 mod p. And this can be easily proved by multiplying a on both sides of the first version of Fermat's theorem. So in order to prove this, we can write it like this, that we will multiply a on both sides of the first version of Fermat's theorem. So this will become a into a to the power p minus 2 mod p, and this will become a to the power p minus 1 mod p. And now this is the first version of Fermat's theorem, so this is equal to 1 mod p. So in this manner we can compute the inverses. So let us take an example to calculate the multiplicative inverse of these numbers. So by using this Fermat's theorem, and we can replace the extended Euclidean theorem to calculate the inverse of 8 inverse mod 17, 5 inverse mod 23 and so on. Another important theorem is Euler's theorem. So it can be thought of as a generalization of Fermat's Little theorem. So in this case, the modulus as compared to the Fermat's theorem, where the modulus was prime number. So in case of Euler's theorem, the modulus can be any integer. And similarly, we have two versions of this theorem. The first version of this Euler's theorem is similar to the first version of Fermat's Little theorem. So if a and n are relatively prime to each other, then a to the power phi of n is congruent to 1 mod n. So where phi n is basically the Euler's torsion function. And the second version is a to the power k times of phi of n plus 1 is congruent to a mod n. So the second version of Euler's theorem is used in the RSA crypto system, which we will discuss in chapter number 10. So let us take few example of using this theorem. So if we suppose we want to find out the result of 6 to the power 24 mod 35, so we can write this as 6 to the power 5 of 35 mod 35. So then it will satisfy the Euler's theorem and the result will be 1. So one more example, suppose we need to calculate 20 to the power 62 mod 77. So in this case, let us assume that k equal to 1, and using the second version we have 20 to the power 62 mod 70. So this can be split like this: 20 mod 77 and 20 to the power 5 of 77 plus 1 mod 77. So this is equal to mod 77. So 20 into 20 mod 77, this is equal to 15. Similarly, we can compute the multiplicative inverses using Euler's theorem. So Euler's theorem can be used to find the multiplicative inverse like this, that A inverse mod n is equal to a to the power phi n minus 1 mod n. And these are some of the examples of using this Euler's theorem to replace the extended Euclidean theorem. Another important theorem which is used in cryptographic functions is Chinese remainder theorem. So this Chinese remainder theorem is used to solve a set of congruent equation with one variable but with different moduli, which are relatively prime to each other. So here we need to find the value of x that is congruent to different moduli m1, m2 up to mk, and the condition is that m1 up to m2 up to mk, they are all relatively prime to each other. So this here is an example of a Chinese remainder theorem. Suppose we need to find the value of x, where x is congruent to 2 mod 3, x is congruent to 3 mod 5, and x is congruent to 2 mod 7. So this 3, 5 and 7 are relatively prime to each other. So let us try to solve this theorem or equations. So these are the steps of Chinese remainder theorem. So first of all, we need to find a common modulus capital M that is equal to the product of small m1 into m2 up to mk. Then we will find capital M1 equal to m upon m1, m2, m upon m2, and so on up to mk. And then we need to find out the multiplicative inverses of m1, m2, mk using the corresponding moduli, that is small m1, m2 up to mk. And we will call these inverses as m1 inverse, m2 inverse up to mk inverse. Finally, the solution of the simultaneous equation is like this, that x is equal to a1 m1 m1 inverse plus a2 m2 m2 inverse up to ak mk mk inverse, and on the total we will take mod of capital M. So now let us try to solve this equation. So the first step is calculation of capital M, that is equal to the moduli 3 into 5 into 7, that is equal to 105. Then we will compute m1, that is 105 by 3, m2 is equal to 105 by 5, and m3 is equal to 105 by 7, and we will calculate the inverses using these individual modulus. And finally the result is like this: x is equal to this much, that is equal to 23 mod 15. So let us take one more example. Find the integer that has a remainder 13 when divided by 7 and 13 and but is divisible by 12. So we can write this statement in terms of three equations, that x is equal to 3 mod 7, x is equal to 3 mod 13, and x is equal to 0 mod 12, since x is divisible by 12. Now we can apply the Chinese remainder theorem, and the solution will come out to be x is equal to 276, and then we can check our answer by placing this 276 into these three equations. So let us take one more example. Suppose we need to calculate z equal to x plus y, where x is equal to 123 and y equal to 334. So and this has important applications. For example, suppose we have a system that accepts only integers less than 100, but in this case you can see that x and y both are greater than 100. So what we can do, we can split these equations into two forms, that x is congruent to 24 mod 99 and 25 mod 98 and 26 mod 97. Similarly, we can split y as 37 mod 99, 4198 and 43197. Now we can add up these congruence to find out this x plus y is equal to this much, and instead of x plus y we can write in terms of a single variable z. Finally, we can calculate the value of z using Chinese remainder theorem, and we can find the answer as z equal to 457. So it means that x plus y is equal to 457. Thank you.